Hello, class. Now we are on to something new. So we finished chapter 4, which is on different uses of partial differentiation. And now we are on to chapter 5, which is double and triple integration. So we'll start off nice and simple with double integrals over rectangular regions. So let's begin. Hear, O Israel, the Lord our God, the Lord is one. You shall love the Lord your God with all your heart, with all your soul, with all your mind, and with all your strength. The second is this: love your neighbor as yourself. There's no commandment greater than these. Okay, heart's full, mind's ready. Let's begin. So recall that when we had a function such as f of xy, we can say, well, z equals f of xy. We can graph it like a terrain. And if we can graph it like terrain, then we can find the volume of that terrain um, over top of the xy axis, xy plane. So then the volume of this terrain over the xy axis creates a shape, a three-dimensional shape, and we can try to calculate its volume. And that's what we're going to be trying to do today. We're going to be doing it over rectangular regions at first, and then we'll get to things that are more complicated later. But for this section, all of our regions will be rectangular. So we think about how to find the volume of that. Recall how we talked about the area under a curve in Calc 1. Also, we might have talked about that at the beginning of Calc 2. So the area under the curve has, in that case, you're talking about like adding up all these rectangles. Well, now we're going to add up a whole bunch of things that look a lot like skyscrapers. And so what we're going to do is we're going to look at that rectangular region, and for each rectangular region, pick a point that will represent it. So for instance, this is, say, x star 2, 3, y star 2, 3. And so then in that case, and then so each region is like an Rij. So the area of the region is an Rij. Xi, Xj is kind of at the corner there. At the corner there. And then like the stars represent like my representative point. And so then delta x is kind of like the width of my rectangles. Delta y is the height of my rectangles. And so then for each little rectangle, I can draw like the skyscraper that would go up to where the kind of terrain goes. Although I'm mixing my metaphors now because it feels like I'm like finding the volume of underground terrain above a bedrock, but then I'm using skyscrapers. I don't know. I need to figure out the best metaphor here. But we're taking that volume and then we're kind of approximating that with a rectangular prism. And just like how we approximated in Calc 1, we approximated with little rectangles. Now we're approximating with rectangular prisms. And so the double integral is just a limit as our rectangles get teeny tiny. So m and n both going to 0. I equals 1 to m, j equals 1 to n of all these representatives times the area of the base, because the volume of a rectangular prism, this is the height of my rectangular prism. This is the area of the base. Okay. So, and then we're going to use this terminology when we're doing a double integral over a region. And so in this case, our region is named R. Now, R is a special rectangular region. It's like X components might be from two numbers, in this case, A and B. Its Y components might be two numbers, C and D. So then I could also write it like this, which is kind of an iterated integral. So an iterated integral. And so when you see the double integral like that with the numbers, just like we saw in Calc 1 and Calc 2, then what we really mean is do the inside integral first then the outside. Okay, so we always do inside integral first, then the outside. And then you can go, now in Calc 1 and Calc 2, the dy and the dx didn't matter. Now they really, really, really matter because they tell you which value you're integrating over first. So in this first one, I'm integrating with respect to y first. The second one, I'm integrating with respect to x first. And if I mess that up, I'm going to mess up the problem. Okay, and then our last thing for this introduction is Fubini's theorem. So Fubini proved that if R is a rectangle with x's from a to b and y's from c to d, then the double integral over the region is the iterated integral, and you can do either one first. You can do dy and then dx. You can do dx and then dy. Okay, so that covers the introduction, and we'll move on to the example 1.